Where have you heard terrible sound? Parties, clubs, festivals? Huh? YouTube? Okay, you've heard terrible sound. How would you describe that?
Sometimes there won't be like the higher pitches where you will kind of expect it to be high pitched.
Okay, so there's frequencies missing sometimes. You're listening to something on YouTube and then you like walk into a place with very bad reception and then the quality just drops and it gets like super, I know, squishy and crumbly. It sounds like it's a little bit like it's been under running water, right?
Yeah. People also just upload bad quality sound.
People might upload stuff to video that they just like recorded cell phone video, right? And quality of the sound isn't great. Anything else? Any other places where you've heard terrible sound?
Like AM radio, like long range radio.
Okay. One of the nice things about amplitude modulation is that the wavelengths are long enough that they will actually kind of follow the curvature of the Earth. So even if you don't have technically direct line of sight to wherever that radio station is, that signal can actually bounce off the layers of atmosphere and reach you. And so you can hear them, but they're a long ways away. So obviously there's good things to hear them, but what's the bad things?
I think it just sounds kind of muffled and I guess maybe the frequency component.
Okay, so it's missing some frequencies again, yep. You also find sometimes it's like static, there's hissing in the noise, sometimes it almost squeaks. How about live sound or clubs?
Either your bass is like overwhelming everything else, or you're like it's really above zero on your master, and that's like
okay, so there's distortion and there's too much frequency, too much low frequency. It's not like there's no high frequencies there, but the balance of what should be there is off. There's just way too much bass, which, you know, it's an interesting physical sensation. Sometimes it can be a bit of a nauseating sensation at times. But you clearly get a sense that this is not what the music is supposed to sound like. And then you said distortion. How we describe distortion from a listener's point of view? What does it sound like? Harsher, all right? Hard to make out lyrics.
Harsher, yeah.
What
I was
else?
going to say like the box is emitting, like the hardware itself is making the noise. Like the drums.
It doesn't sound like an instrument. It doesn't sound like a voice. It sounds like a vibrating box, right? Which it is. It is, you know, in many situations, that's what the speakers are, the vibrating box. But clearly the intent isn't to make you think that you're listening to boxes. The intent is to make you think that you're listening to voices and instruments and synthesizers and drums. The sounds are out of phase, where it sounds like the speakers aren't actually moving in sequence, or maybe hearing the same sound, but it's reaching your ears at different times. These are all real problems. Some of these are acoustic problems. These are things that arise when you've got air vibrating inside an enclosed or open space and you're trying to fight with the architecture of a space. I'll save that for Wednesday. Today I'm just going to talk about the electronic side of things. And a lot of these problems do occur in the wires, in the cables, in the hardware, in the PCBs. And the general goal of a sound engineer when they're trying to figure out how loud or how soft something needs to be is they want it to be louder than whatever inherent noise there is in the system. All electrical hardware will have a little bit of noise. That's what we sometimes refer to as a noise floor. There's a certain level of noise that the electronics themselves are generating or picking up from other electronics in the space. It could be other radio stations. It could be the lighting. Fluorescent lighting is pretty bad, usually for that. Halogen lighting is pretty bad. It could be, your phones that, someone's just sending a text message and it generates noise that gets picked up by the wires. Or it could be stuff that's actually in the equipment itself, USB power. The power adapter that's currently powering my laptop is generating some sort of electromagnetic noise. And that's just sort of lingering in the environment. In some cases, that can be engineered out, and often when you're buying electronic equipment, that's one of the things that you're paying for. Right? How much effort have the engineers actually put into trying to reduce the effects of external noise or reduce the impact of internal noise, right, by properly laying out the circuit in a way that minimizes that. For an audio signal, I'm going to draw that as a sort of a bunch of dots. Just lurking in your audio signals, audible as a sort of a hiss. If all the music that you're listening to was originally digitally produced, there might not actually be much of a hiss in there. But if you just turned up your speakers real loud, just turned up the little amplifier knob on your speakers, you'll hear the hiss of all the equipment that's connected to your speakers, and then you actually hear that hiss. So that's what we call noise floor. And in this case, I'm talking very specifically about analog noise. The other situation is a lot of the controllers that you use, they're being powered by USB. Anybody know what the standard voltage for plain old USB-B and USB-A is? 5 volts, right? 0 to 5 volts, that's usually a ground, and then there's a 5-volt line. Which means it's actually really difficult for any of those devices to put anything more than 5 volts. It's not impossible. There are things like buck converters that actually allow you to generate more volts, but most of your devices don't have those. Plus 5 volts, and you have a ground, and your entire signal has to live somewhere in between these two. That's all the voltage that it's getting from the USB port, and your entire device is being powered through that. Plus, audio signals go up and they go down. They oscillate, right? So they don't go below, they don't go minus 5 volts. They kind of just do this, and then it needs to get like normalized somehow. So often, a lot of these circuits actually have 2.5 volts, minus 2.5 volts, and ground. This is what's coming out of a lot of your USB-powered audio devices. This is what's coming out. The good news is that this is actually pretty much to spec. Nominal voltage is closer to something like 1.7 volts for pro gear, but you see audio gear that gets to 2 volts and in excess of 2 volts pretty often. 2.2 is actually not an unreasonable number, it's a fairly loud number. So you've got this extra kind of like 0.3 volts to play around with, just in case, say, your drum is a little bit too loud, you can sort of like exceed it a little bit, and you'll still be fine. This extra little distance that you get between your nominal voltage levels and what your equipment is actually capable of putting up, that's called headroom. Which is kind of like the amount of overpowering that you can do without affecting the signal. But there is a limit. You've got that 2.5 volts up, you've got that minus 2.4 volts down. What happens when that signal gets past your available headroom? So we're amplifying this to the point where we're way past our available headroom. So what could happen to the signal? Yeah. You could clip it like that, right? The equipment has no more additional voltage to provide. This is all it's got. You can think of a lot of audio equipment as kind of a valve that's actually just letting power from whatever power source you've got, in this case USB, and just like letting it out into your speakers. You can go up to 2.5 volts, you can go down to minus 2.5 volts, and we're going to let that out. If it's a quiet sound, we're just going to let a little bit of that power through. And it's a very loud sound, we're going to let a lot of it through in some sort of oscillation. But at some point it can't, and it can clip, which means instead of a nice curved sine wave, we've now got something that looks a little bit more like a square wave. All right? And some of you play music with a lot of square waves, and you know what it sounds like. It sounds very harsh. We used that word earlier. So this is one form of distortion. And distortion is just a catch-all term to describe the wave that we put in isn't the wave we're getting out. In some cases, it can be pleasant, actually, or it could be a desired effect. Anyone play electric guitar? The distortion guitar is kind of like the classic sound of rock and roll. It started off with just electrified guitars playing way louder than the speakers could possibly handle. And instead of getting a nice twang that you would get from an acoustic guitar, you get this like fuzz. You get that fuzzy sound, which eventually becomes like, the grindy sound that you get with heavy metal. And that's a desired effect, right? They're deliberately doing this to the guitar sound. There's another thing that sometimes happens with pretty high-end analog gear, which is called saturation. Instead of just a hard clip, they actually have some sort of like non-linear behavior just as you get close to that edge. So maybe it's just a matter of it rounds it off so that it doesn't quite hit the top. That's kind of in between a square wave and a sine wave. And again, you get some sort of like fuzzing. You get these additional frequencies that weren't originally there, or at least our ears are perceiving that as such. And that's called saturation. And if you listen to a lot of lo-fi channels, you've probably heard saturation. Magnetic tape does this a lot. So if you're recording to magnetic tape and you're recording at a level way past spec, the way how the sound distorts is often described as saturation. But also, as you're amplifying it that loud, all of your noise also gets amplified. So now, instead of like a fairly low-level thing, we've got this really, really wide, patchy field of noise. And all we're trying to do is we're trying to minimize that while we're trying to use what available headroom we've got to get a good audio signal. When we're doing a recording, we're trying to make sure that our sound is not so soft, where we finally turn up the volume and I can actually listen to it on our headphones or on our speakers. You're not just hearing a pile of hiss. But it's not so loud that we're getting a bunch of distortion. All right? That's the goal. This kind of noise that I'm describing over here is kind of the analog domain. If you have a digital signal, and a lot of the music producers nowadays, their instruments never existed in the real world. It was always a computed waveform that came out from a computer. You might not actually have this sort of noise. If you think of a digital waveform as basically a bunch of points, right? Something like that. That minimum distance between where each point could be actually generates a sort of noise that can be audible if you made it loud enough. Because, say I have a 16-bit wave file, which is what you find on CDs and probably what most MP3s are encoded at. 16 bits. How many integer values do we have in 16 bits? 2 to the power of 16. What is 2 to the power of 16? Yeah. Very nice. So 65,000-ish, but we get half of that above 0 and half of that below 0, right? So it's more like 32,000 integer levels above 0, 32,000 levels below 0. Let me turn this into a bit of a grid. Say we've zoomed into a digital recording of something like a crash cymbal that's slowly fading out, right? There's just that last note in a song. And what the analog wave was supposed to do is this, right? So over here, it's probably still going to be fine. And then around about here, we're going to have some trouble reproducing this part over here. Either it just cuts out into silence all of a sudden, or we get some rounding errors. It sort of like jumps up here. And if you've got large enough sound system, like in a club, these sounds can actually become audible as a kind of like kind of thing. And that's called quantization noise. It just basically makes things like long trailing notes sound really, really bad as they trail away. It's usually not a problem when they're being loud, but when they're being soft, you can actually perceive that noise. One cool thing that a lot of commercial releases of music will do is they'll add this thing called dithering, which is basically they'll just add a layer of noise, And yeah, you would think that will technically make the signal sound worse. But actually, when it comes to things like long trailing notes, it actually allows those notes to fade off into a clean sort of fade out, instead of buzzing as it goes out. And so instead of hearing quantization noise, you just kind of hear this much more analog-y kind of noise. And it's actually pretty nice. Now, these are all things that are happening at such a low level that unless you've got your amplifier turned way up, you're probably not actually hearing it. But if you're a music producer and you've got drums and you've got a piano and a guitar and a voice and synths and all these different instruments, and all of them are adding their own little bit of noise to it. Some of them are acoustic instruments that you've recorded or singers that you've recorded. Some of them are being synthesized. all those cumulative effects can pile up to the point where your finished recording actually makes it audible. Now, this is not really a problem that you have to worry about for assignment 2. Quantization noise is usually the sort of thing that is more worried on the music production end. I just want you to be aware of it if you're interested in going into music production in the future. This is a digital form of noise. This doesn't make sense unless you're working with digital sounds in particular. Because if your digital sound is just a bunch of zeros, no matter how much you amplify that in the digital domain, it's just still going to be a bunch of zeros. You're not going to get any additional noise on top of that, unlike analog noise. So you don't get that kind of like regular speckling kind of noise unless the sound was originally recorded using analog hardware in the first place.